Hello, everyone. My name is Yuan. I'm a software engineer from Intel Machine Learning Performance team. Today, we will introduce our new project called Native SQL Engine for Spark. I will give a short introduction on the background and the general architecture. And my colleague Chen Di will help to introduce more details for this interesting project. Okay, so this is the agenda today. First, we will do a general introduction on our Native SQL Engine, our motivations for this project, and the general architecture. Then we will dig into those details. There are three big components in this project. The first one is we build a columnar data source. The second one is columnar shuffle. The last one is the biggest one, columnar compute. So Spark SQL works great in today's. But we still saw there are several disadvantages for Spark SQL. First one is it's using an internal role-based format. It's very difficult to optimize with SIMD optimizations like AVX2 or AVX 512. The second one is since Spark works on JVM, the GC overhead is very, very difficult to handle. You have to tune very carefully on this if you are working under low memory. The third one is the JIT code greatly relies on JVM. It's difficult for engineers to tune this because it's inside JVM. Last one is Spark didn't have a very good framework to reuse those native libraries. For example, we have many good native libraries on different parts. For example, for sort and for Hashmap, we have many good libraries, but it's difficult to use these libraries inside current Spark. So to solve these issues, we are proposing a native SQL engine. First, we introduced columnar-based arrow format. The right picture is actually a famous picture from Arrow community. As you can see in the picture, traditionally, Spark uses internal role-based format, which means data with different types are merged into one row in your memory. This makes it's unfriendly for CPUs. But with Arrow memory format, the content with one type is placed into one column. So this is much friendly for CPUs. We will introduce these in later slides. The second advantage is we are doing our compute in native codes, so there's not much work inside JVM. So the GC overhead is not an issue here. The third advantage is we introduced generic code generation framework, which can take C++ code and also LLVM IR code. This makes much easier to check the code generation performance. The last bullet is we also introduced lightweight GenAI core framework, which allows the user to use different native libraries very easily. Okay, so this is a very general picture for our native SQL engine. As you can see in the picture, there are three different layers. In the application layer, we didn't do any changes in the application layer. So all existing applications like Spark SQL or Java Scala apps can run on native SQL engine without any modification required. In the middle layer, we introduced a query plan optimization. So with this layer, it can generate the optimized plans for our native SQL engine. In the bottom layer, this is the core part of our native SQL engine. There are three components here. The first one is called Native Arrow data source, which can read data from different file system with different format. For example, it can read parquet files with native code and then generate arrow-based columnar format and feed into our native SQL engine. The second one is our native compute operators. So in this part, we have implement many operators as well as those expressions. The core part of this compute is done with Arrow Gandiva and also pre-compiled kernels with C++ code. The third one is a Native Shuffle. We implemented a new shuffle with Arrow record batch based. These three big components are the core part of our native SQL engine. Also, there are some small parts, but it's also very important, like memory management. We were generally introduce these components in details in the following slides. Okay, so I want to mention several key points here. The first one is data format. As you can see in the picture, initially Spark used internal role-based format, which makes it's unfriendly for CPU caches. And then in Arrow format, we are using a new format called column batches, which is a fixed size batch, but with columnar format. But in our native SQL engine, we are using an optimized version. So during the benchmark, we found the batch size is critical for different platforms. If you have a high-end CPU, you may want to increase the batch size so that the performance can be much higher. But if you have a low-end CPU, you may want to use a smaller batch size so it works better on your CPU. So in native SQL engine, we have developed a tunable batch size for our all of our operators, and it can automatically split and collapse batches between those operators. Okay, the second idea is Spark plan rules. So this is a very famous picture in Spark SQL world. The above picture is a execution flow for traditional Spark SQL, and the bottom picture in the page is the new working flow for our native SQL engine. As you can see, the difference is only in the query execution part. In native SQL engine, we didn't touch anything before physical plan generated. After physical plan generated, we will do some slight modifications on the plan. For example, we will insert our columnar operators. We will try to do Columnar Whole-stage for those different operators, and we also will try to do the adaptive query execution here. Okay, this is the third point. This is a Columnar Whole-stage concept. So initially, when we implement these features, we first implement those more operators, like in the left picture. It's working like operator by operator. We then realized those performance is not that good because there are many materialization overhead between those operators. Then we added the Columnar Whole-stage feature, like in the right picture. As you can see, we can actually group those joins and aggregate into one native operator so that the materialized overhead is removed. The performance is much better than the left picture. Okay, so let's go to the details here. The first one, I will introduce the data source. So the left picture is for today's Spark. although Spark has a vectorized parquet reader, but it still compute based on its internal row format. So eventually, Spark will need a column to row conversation between those operators. So with our native SQL engine, we are using Arrow record batch based data source. It can actually reading from different file formats from different data sources. It's very fast. So this picture is the working flow for our data source. The application layer is unchanged. So existing workloads on PySpark, Thrift Server, Spark SQL can running with data source without any modifications required. In the underlying part, we are actually using Arrow dataset API. It's very efficient because it provides zero data copy feature. And in the underlying, we are using C++ code to fetch those files from HDFS or your local FS or even S3. Okay, so this is the features for columnar data sources. We support different file systems like S3, HDFS, or local FS. We also supported push-down support with statics or metadata filters. As of today, partition files are also supported right now. So the dynamic partition pruning feature is also supported. Okay, so this is a general introduction for our Columnar Shuffle. The first thing is since we are using Arrow record batch based, it will try to split those Arrow record batch with native LLVM optimized execution. Since we are on native side, we can do very efficient data compression based on different data format. For example, for integers, we choose one format. We choose one compression algorithm, but for string, we can choose another one. So it can achieve better efficiency. On the reducer side, we will automatically do a defragmentation on those shuffle files so that we can get a better batch size to feed into the following operators. Also, the adaptive query execution feature is supported in our columnar shuffle. Okay, with that, I will hand to Chendi. She will give a detailed introduction on the operators.
Thanks, Yuan. In this page, we shows all operators and expressions currently supported in our project. And we covered our TPCH and TPCDS queries by blowing operators and expressions. And one thing need to mention here is we will convert a Spark expression to Arrow Gandiva expression in our colonized Spark plan, since Arrow Gandiva expression can be passed to native side for later on native process. And during the conversion, we also can detect those expressions we are not supported yet. So we can do the automatically fallback to make all queries run. Let's move on to the Columnar project and the filter. Let's take an example. A project is something like this. We added fields A, B, C together and compared with field D. And if the results is greater than D, we return this row. And if the results is less than D, we just abandon this row. And an expression like this will be passed by Arrow Gandiva to native side. And then we will use LLVMIR to, we will compile into LLVMIR. Since the input data is using columnar batch format, the LLVM function can core will process a vector of data at once, leveraging AVX instruction sets. Then let's talk about Hashmap. There are two types of Hashmap in our native SQL engine project. One Hashmap is much like Spark, and it's Spark compatible 32-bit hash algorithm with a original role to handle hash collision. This kind of hash map will be used in hash partitioning and broadcast hash join. Then we also implement another advanced type hash algorithm using 64-bit hash with a sparse layout. This hash algorithm will better leverage AVX to generating hash key, and also did much better in probing in Hashmap. And meanwhile, using 64-bit hash algorithm also significantly reduced hash collision chances in probing, so performance is more optimal. And this type of hash algorithm will be used in hash aggregation and shuffled hash join. Then let's take a look of the broadcast hash join exchange data. The broadcast hash join exchange data consists of two types of data, a hash map and the original Arrow record batch. In our design, we didn't copy the original data into the hash map because there can get two benefits. Firstly, it eliminates redundant memory copy from colonized format to hash map. The second benefit is using colonized format to broadcast data. The data size will be more compact and capacity efficient compared with row-based hash map. So another benefit is also can be when broadcast exchange is used by semi-join or anti-join or existence join without any condition check. We can easily only send out hash map instead of the hash map plus Arrow record batch combo. Let's now talk about sort and sort merge join. So in most TPCH and TPCDS cases, sort are used for sort merge join. So our implementation of sort is also be optimized for sort merge join case. So there are three types of implementation of sort. The first type of implementation is for those data with only one field of key and without any payloads. This type of sort will be mostly seen before semi-join, anti-join, and existence join. And for those type of data, we will use in-place radix sort. So the sort will be AVX optimized. And the second type of implementation of sort is for those data with one field of key and with multiple fields of payload. And that type of sort, it will be mostly seen in inner join and outer join. So for that type of data, we will also use radix sort, but instead to put the data in place, we will use indices in the sort memory and use the indices for later maturization. And the third type of sort is for those data with multiple fields of key and multiple fields of payloads. And to implement that type of sort, we will do code-generated quick sort and put the indices in sort memory. So since sort is the input for sort merge join, instead of materialize those sorted data, we will only input the indices to sort merge join. And then we will use the index from the indices array to access original data and do a project comparison and a condition check to those data, then materialize those index being selected. Okay, then in previously slides, we talk about individual operators implemented in our project. And in this page, we will talk about WholeStageCodeGen. For Spark, after SQL plan being analyzed, there will be multiple stages and multiple operators in one stage. And Spark doing a WholeStageCodeGen optimization to create a big while loop and put code block from different operators in this while loop. And our idea of Columnar WholeStageCodeGen is quite similar with what Spark did. The difference will contains below 2 points. Firstly, we will build our WholeStageCodeGen in C++ and compiled with GCC. By doing that, our code will be easily compiled with vectorized instructions. Secondly, as you can see, we also do WholeStageCodeGen for shuffled hash join. The reason for that is our hash map is managed in native memory, so the allocation and the release will be much easier than using JVM, since the garbage collection overhead will be eliminated. And also, since we are using Arrow data format, the memory will be more compact and capacity efficient. So we introduced our components like SQL computing, shuffle, and data source. These components are located as the base of our project. For example, project and filter will use existing Arrow Gandiva, and the WholeStageCodeGen multiple key sort, and shuffle join with condition will use C++ code generator kernel, and remaining operators will use compiled template kernels. So to integrate our project into Spark, we also implement 2 layers above. The top layer is written by Scala and Java to convert Spark expressions to Gandiva expressions, so we can pass them to native side. And then we also need use the top layer to treat columnar batch as the intermediate data between RDBs. The middle layer is a GNI adapter, which is to build Gandiva expressions to different kernels. So this layer is easily to be extended to hook more libraries. Okay, then let's talk about memory management. So there are 2 types of view in this picture. The above view is a workflow view, and the below view is a memory pool view. So in the above view, from the workflow view, there are 2 types of data: intermediate data and internal data who need to use memory. So the intermediate data is what in Spark, the intermediate data is unsafe row, and in our case, intermediate data is columnar batch. For example, the first operator, the data source operator, will read data from underlying file system, then allocate an arrow record batch, then pass the arrow record batch to the next operator, which is called a project. Then the project operator will evaluate the input arrow data and generate and allocate a new one to pass to the next operator. So the intermediate data can be allocated and released between operators. Then for some operators like sort, we don't want to release the data immediately after evaluation. We want to keep them as long as possible until spill is triggered. In that case, we want to retain those data as internal data and release when task is completed. So in the task completion hook. Besides input Columnar batch, Hashmap is also treated as internal data. So despite its internal data or intermediate data, it's all from 3 different memory pool: JVM pool, direct memory pool, and the native memory pool. The later 2 memory pool are managed by Arrow Allocation Manager, and they will be registered to Spark Task Memory Manager and get grant to allocation from Spark, and also being notified for any spelling instructions. Okay, and this is a snapshot of a demo example of TPCH Q4. As you can see, all operators in this page are converted to columnar operators. From our initial evaluation, we observed about 30% performance improvement in 1.5 terabytes TPCH datasets compared with original Spark with same configuration. Okay, and that's all about our project. And if you are interested to know more about our project, please visit our repo on GitHub, written in these slides. And for now, our project is under intensive development. All TPCH and TPCDS queries are runnable and shows big improvement.